All right. Okay, so today we're going to try to get through, I'm not sure if I'm going to be able to finish completely my discussion of the Ramsey Neoclassical Growth Model, but I do want to get through most of it. We will conclude our discussion of this phase diagram that we began constructing in the last class. And then we will at least start a proof of the existence and uniqueness of the so-called saddle path solution to this problem. All right, so let's just kind of review where we finished in the last class. We characterized the steady state equilibrium of the Ramsey model, and then we wanted to discuss the transition dynamics, meaning given some arbitrary initial value of capital, how does the economy evolve over time towards the steady state? The analytical device that we want to use to think about those transition dynamics is this phase diagram. And so we did that in capital consumption space. Now, hopefully you guys remember this, but the two key, I should have written this down, the two key equations of the model, I'm going to write them down just here below my picture, are going to be that help us construct the phase diagram are going to be one, the intertemporal Euler equation, right? Marginal utility of consumption today is the discounted value of the marginal utility of consumption in the next period times the gross real interest rate. And the second equation was the period by period solvency condition or resource constraint, which says that capital per worker in the next period, adjusted for growth in the population, had to be equal to whatever was produced this period, plus whatever capital remains after depreciation, minus what agents decide to consume. So these two equations, together with a transversality condition or a no-Ponzi condition in strong form, fully characterize the competitive equilibrium of this model, that is, sequences of C's and K's over time. We use these two equations to construct two different locus of points in KT-CT space that together would demarcate the region of the space into four parts, region A, B, C, and D. And then what we can do is we can analyze the dynamics of consumption and capital jointly within each of these regions, right? So first we constructed this thing that I called the KT is equal to KT plus 1 locus of points. You guys recall what that is? This particular curve in KT-CT space shows all the combinations of KT and CT that are consistent with the capital stock being stable over time, that is from periods T to T plus 1. Therefore, if a steady state exists, which we know it does, it must lie somewhere on that particular locus of points. We derive that using the resource constraint 2. This other locus of points we call the CT plus 1 is equal to CT locus. In other words, it showed all the combinations of K and C in this positive quadrant that were consistent with consumption being stable over time, fixed between periods T and T plus 1. Again, if a steady state exists, which we know it does, it must lie somewhere along this locus of points. Well, you can see that in their construction, the two loci only intersect at one point, and that's where the steady state must be located. So the intersection of these two things gives us the steady state level of capital and the steady state level of consumption, which we can characterize on the phase diagram as well as analytically by evaluating these two conditions here in the steady state. Okay. Now, I think to close the class last Monday, or this past Monday, We also examined how the paths of consumption and the capital stock must look like in each of these different 4 regions, right? And what we discovered was that if we were at a point in region B, that is, if we were at some KT/CT that happened to lie up here in this region, that consumption was going to rise and the capital stock was going to fall over time. So between periods T and then T+1. So this is a snapshot of what's happening in period T. If we were to look to see what happens in period T+1, then we would be at a point somewhere northwest of this point, right? We're moving in that direction. In region D, we're moving in the southeast direction. In regions A and C, however, in region A, we're moving northeast, and in region C, we're moving southwest. So by analyzing the dynamics within each of these different regions, we can kind of see what the stability properties of the model are. Now, let me again make one thing perfectly clear. Depending on what point, if you just pick an arbitrary C and K in this space somewhere, the subsequent trajectory that it's going to take, if you're up here, it's going to go here. If you're down here, it's going to go in this direction. All of those trajectories, paths, are fully consistent with equations 1 and 2, which are 2 of the optimality conditions in the model. And there's an infinite number of possible trajectories, right? You've got all these lines that kind of do this, right? And a bunch of lines that do this. There is only one path, however, that leads directly to the steady state, called the saddle path. So for any arbitrary initial value of the capital stock, let's say K0, what this says is that there's only one value of C0 such that the subsequent path of capital and consumption is going to lead us eventually to the equilibrium steady state point, let's say point E. If initial consumption is any larger or any smaller than C0, then you're eventually going to be led into region B or region D. And what we're going to try to establish today is that even though all of these infinite number of possible trajectories is consistent with equations 1 and 2, there is only one trajectory that is actually consistent with the 3rd key condition in the model, and that is the transversality condition. In order for the transversality condition, that is the no Ponzi game condition, to be satisfied in equilibrium, initial consumption must be such that we jump up to this saddle path solution and eventually transition to the unique steady state. So whereas the Euler equation and the intertemporal resource constraint tells us what the optimal values of C1 through C infinity are going to be, what is it that determines the optimal value of C0? It's the transversality condition, right? That is the lifetime budget constraint, which depends on the net present value of initial wealth plus lifetime labor earnings. Those things don't matter for the subsequent path of consumption and capital. That's what we want to try to prove today. Now, before we do that, let me talk about this picture a little bit more. Without losing my spot in the notes here. You will notice that I have drawn this phase diagram in a way such that the steady state value of capital is actually less than the golden rule. I want to spend a little bit of time talking about that today. First, I want to prove that that must be true, which is really easy to do, and then talk intuitively about why it must be true. Now remember, what is the golden rule level of capital? We learned this in the context of the Solow model. It's the steady state level of capital such that what is satisfied. It's the golden rule level, it's the one that maximizes consumption in the long run, okay? Now, in this model, utility depends on consumption only. So it makes some sense that if households are behaving optimally here, wouldn't they want to ensure a long run equilibrium where consumption is maximized? But actually they don't. The steady state level of capital is less than the level of capital that is consistent with the highest possible value of consumption in the steady state. That is the peak of this the peak of this KT plus 1 locus. Okay, well, let's first do an easy proof that establishes that K star is indeed less than the golden rule. What's the steady state condition for the capital stock? You guys recall? The marginal product of capital in the steady state was equal to the discount rate plus depreciation, right? What is the golden rule condition? You guys remember? It's where the marginal product of capital was equal to
N plus the discount rate.
Sorry?
N plus the discount rate.
Not n plus the discount. Yes, delta plus n. Exactly. Sorry, I misheard what you said. So the marginal product of capital is equal to the depreciation rate plus the population growth rate. That's where the golden rule level of capital is. So if we compare these two, what do we see immediately? That f prime of K star minus rho is equal to delta. Well, that's also equal to f prime of the golden rule level of capital minus n, right? Which means that f prime of K star minus f prime of Kg has to be equal to rho minus n, correct? What do we know about rho minus n? What do we know about the size of rho relative to n? It has to be positive. Why? By assumption. Remember? I believe it was assumption 2, which said that rho had to be bigger than n, because that's the only way we get proper discounting in the lifetime objective function, right? This was a critical assumption in the model. So rho, we're assuming, is bigger than n, which means that f prime K star minus f prime at the golden rule is bigger than 0. Well, that means the marginal product of capital at the steady state is bigger than the marginal product of capital at the golden rule. The production function is strictly concave. So that implies then what? That K star is strictly less than the golden rule level of capital. So the very fact that we impose proper discounting on this model is going to ensure that the steady state level of capital is less than the golden rule level of capital. Now, why does that make sense intuitively? Why would the representative household ever want to implement a consumption plan over time that would lead to a level of steady state consumption that is less than the golden rule, that is the highest possible attained, the highest level of consumption attainable in the model?
They're oversaving.
They're not oversaving. If they were oversaving, they would accumulate capital more than the golden rule. They're undersaving, right? But why? Why is it optimal to, in a sense, undersave? In the OLG model, then, you can oversave and accumulate capital in excess of the golden rule. And that was this dynamic inefficiency. The dynamic inefficiency in the Ramsey model is ruled out because rho is bigger than n. And rho is also equal to the steady state value of the real interest rate, right? It's telling us that the steady state capital stock has to be less than the golden rule. What does the representative household care about here?
Maximizing consumption.
Nope.
No.
The representative household cares about maximizing the lifetime objective function, which is what? It's the sum of current utility and all discounted future utility, where utility depends on consumption. So what is more important to the representative household? Near-term consumption or future consumption? Near-term consumption, because the representative household is discounting the future. So the decision maker here, Ben, is not seeking to maximize steady state consumption. She's seeking to maximize lifetime utility, where lifetime utility weights more heavily near-term consumption relative to consumption in the long run. That is the steady state. Okay? Think about this. Imagine, Ben, we were at point E, and the representative household says, I want to get to a point where we have permanently higher consumption forever. That is, I want to go from this point to this point. In order to get there, you would have to increase the capital stock, right? But the only way to increase the capital stock is by doing what to consumption in the short run? You can't increase the capital stock unless you're willing to sacrifice some current consumption, right? So to go from point E to the maximum attainable level of consumption, your consumption path in the short run would look sort of like this. If I were to sketch it on a graph, let's imagine we're at the steady state, and then all of a sudden, if we want to save more, consumption would fall, and then over time it would rise to a permanently higher level, right? This is essentially what the path of consumption would look like. Well, far out into the future, it's helpful to have all of this extra consumption. But what is the trade-off? In the near term, you're going to end up having lower consumption during the transition period, right? You can't get to higher consumption unless you generate more capital, which requires sacrificing some consumption in the near term. Now, because of discounting, what this says then is that, what is that noise? Is somebody drilling something?
Sounds like it.
Oh. Because of discounting, there's going to be a upper bound essentially on how much more utility you can gain by trying to raise consumption permanently. In other words, at some point, what you gain by raising consumption permanently is not going to be enough to offset the losses in utility that you experience in the short run because of the reduction in consumption, right? If you lower your consumption by $1 today, that's more painful than the enjoyment you get by raising your consumption by $1 at some point in the future because of discounting, right? And so because of that, the optimal level of consumption in the long run is actually a little bit less than what the so-called golden rule would suggest. And that's why the capital stock is less than the golden rule in the steady state. They call this, by the way, the modified golden rule. I guess I'm just going to have to put up with that for the rest of the day, huh? Okay. So that's why I wanted to talk about that, so that you guys understand why the steady state level of capital is actually less than the peak possible level of capital in this model. So when you guys are drawing these things on your exam, make sure that this intersection point here occurs to the left of the apex of the KT is equal to KT plus 1 locus. It has to, for a very strong theoretical reason. Okay, y'all have any questions about that then? All right, let's do the following. I want to focus on this graph a little bit more here, and I want you all to consider what the possible trajectories for consumption and capital are going to look like if we start from kind of an arbitrary initial value of consumption and capital. All right, let's take a point, for instance. I'm gonna pick a point right here, let's say. I'm gonna call this point 1. In other words, without loss of generality, this is our initial value of capital in the economy. This is what we're endowed with, okay? Now let's pretend for a moment that initial consumption is way up here at point 1, all right? According to the phase diagram, what is going to be the subsequent path of capital and consumption in this model? What direction are we going to move here? We're in region B, right? Where the capital stock is falling and consumption is rising. So if we start at this point, we're immediately going to move in this direction, right? Where the capital stock continues to fall, but consumption is rising somewhat. So if we're here in this period, in period 1, we're going to be somewhere like over here.
Is there a way, like a proper way to describe that, like say like northwest or like?
Yeah, you could just, right. I don't know exactly. We don't have enough information in a model that's not parameterized with specific values to know which is moving faster. Is consumption moving faster than capital or whatnot? But yeah, it's just moving. You can think about it just moving northwest. Ben? What if instead we pick this point? So let's call that point 2. In other words, our initial value of consumption was such that we were directly on the KT plus 1 locus in the initial period. I want you guys to think about what the subsequent trajectory of capital and consumption are going to look like. Well, we're above the CT locus, right? So when you're above the CT locus, consumption is rising, but we're right on the KT locus. So what's happening to the capital stock between period 0 and period 1 here? Nothing. So in fact, we're going to move from period 0 to 1 just due north, where consumption rises, but there is no horizontal movement in the capital stock. The capital stock does not change between period 0 and period 1. But then as soon as period 1 rises and consumption is higher, so we're now above the KT locus, we're going to do this, right? Let's take a point that's right below the KT locus. I'm going to call that point 3. What is the subsequent path of consumption and capital going to look like here? Well, what region are we in?
We're in region A.
We're in region A. So instead of moving northwest, Tavoy, we're going to move northeast, right? However, we are so close to the KT plus 1 locus that we're going to cross that threshold before we get to region D or the steady state, right? Now, as we cross this threshold though, what's happening to the capital stock? Remember, when we're on the KT locus, the capital stock is not changing. This means that as the trajectory crosses this KT plus 1 threshold, it must do so at a perfectly vertical position where the capital stock is not changing between periods T and T plus 1. But then again, once consumption is higher than the KT locus, we're going to start moving northwest again. You guys see what's happening here? For any initial value of consumption in this region, you're either going to be moving northwest immediately, or you'll be moving northeast, but you'll cross this locus pretty quickly and then do this, right? So all of these trajectories are essentially doing this. And it's important to understand that each of these trajectories that have a different arbitrary initial value of consumption are fully consistent with 1 and 2. They satisfy 1 and 2. They just don't satisfy one of the other optimality conditions of the model, which we'll hopefully start proving here in just a few minutes.
So does proximity to the locus affect the rate of change there? Like you said, it kind of like starts arcing up towards there.
Yes.
Because it's closer.
But yeah, I specifically drew this 0.3 here to be close enough to the KT locus that that trajectory will cross the KT locus before it comes over into region D.
So is the saddle path being like pulled equally by?
Well, let's talk about that. Let's do a 0.4 here. So Ben, if we're at, let's say initial consumption is down here at 0.4, it's pretty low. Then we're in region A, right? So consumption is rising and the capital stock is rising, but unfortunately we're close enough to the CT plus 1 locus that we're going to cross over into region D before we move into region B, right? Now, what do you think the trajectory looks like as we cross this threshold? It should be perfectly horizontal. Why? Because consumption is not changing over time if you're on the CT plus 1 locus. So any trajectory that crosses this locus has to do so at a slope of 0. Okay? Now, I didn't quite draw that correct. Once we cross the CT locus, however, we're in region D, right? And so what direction are we going to be moving then? We're going to be moving southeast, okay? Now, Ben, to answer your question a little bit more specifically here, the CT locus and the KT locus are continuous functions of the capital stock and consumption, right? We're dealing with continuous functions here. That means that if you've got points that are low here that eventually spill over into region D, and you've got points high here that eventually spill over into region B, there's got to be only one point that is going to reach point E before you spill into region B or region D. That particular point, of course, is the optimal level of consumption. I'm going to call that 0.5. And if we start at 0.5, we're going to move northeast, okay? But it's just going to be high enough such that we don't spill into region B before we spill into region D, meaning that it's going to converge exactly to this steady state point. It's because these loci are continuous functions of the capital stock and consumption that eventually at some point you're going to have only one trajectory that gets to a single point before it spills into one of these other regions. And that particular path is the saddle path, which is the one that is satisfied or actually characterized by the family's lifetime budget constraint, i.e. the no Ponzi game condition, i.e. the transversality condition. right? So this is basically a visual kind of informal proof of the existence and uniqueness of the saddle path. That it must be, if a unique equilibrium exists and it is stable, which we know is true because the allocations in this model are the same as the ones from the optimal growth model, then what we're saying here is that for some given amount of initial capital, consumption must jump directly to the saddle path. If initial consumption is just an epsilon higher, then what's eventually going to happen? The path of consumption and capital stock are going to eventually be in region B. If C0 is just a little bit lower than 0.5, then consumption and capital are going to eventually spill into region D. There's only one value of initial consumption that puts us on a path that gets to the steady state, and that is the unique saddle path solution. I think there's an interesting review question that simplifies the Ramsey model enough to actually characterize the saddle path analytically. And it requires that the wage and the real interest rate be constant over time. If you allow the factor payments to be constant, then you can get an analytical solution for lifetime earnings and characterize analytically, that is a closed form solution for the saddle path. That might also help you kind of understand what it is. Okay, you guys have any questions then about that? So again, that's kind of what I would argue is a informal graphical proof of the existence of a saddle path. And by the way, I should point out that there's also several review questions that discuss what happens to the Ramsey model in the steady state if there's a sudden change in one of these exogenous parameters. These are comparative static exercises, right? What happens to the steady state if there's a change in the discount rate or a change in the depreciation rate? Or a change in the population growth rate, or a change in the level of technology? Then you might imagine that what happens here is that one, if not both of these two locus of points is going to shift. And if you start, which means that the saddle path solution is going to shift up or shift down. So if you were to start from the initial steady state, you then can determine something about how the economy transitions to the new steady state by looking at how the saddle path, the new saddle path, compares in relation to the old steady state. It might be the case that if the steady state capital stock increases, you would jump up to the new saddle path immediately and then start to converge, right? So what would happen then is that consumption would adjust at the moment the change occurs, and then the capital stock and consumption would go on a subsequent path towards the new steady state. Or the saddle path might shift down, depending on what is going on in the problem. But my point here is that you can do these comparative statics analytically by taking the partial derivatives, but you also should be able to see what's going on visually by looking at how the phase diagram is affected, right? Remember, there were equations that determined what these two locus of points look like. If there's a change in one of those exogenous parameters, the whole locus of points is going to shift. The slope might change, the intercept might change, etc. Okay, so this leads me then to proposition 4. In the neoclassical growth model, with assumptions 1 and 2 from the solo model, meaning that the production function is neoclassical, as well as assumptions 1 and 2 here, meaning that the utility function is also neoclassical, and that rho is bigger than n, so we have proper discounting. If all of those assumptions are satisfied, then there exists a unique equilibrium path starting from any arbitrary initial value of capital that converges monotonically to the unique steady state. K star C star. If initial capital is less than the steady state, then capital increases monotonically towards the steady state, as does consumption. If initial capital is bigger than the steady state, then both capital and consumption decrease monotonically towards the steady state. So we have global asymptotic monotonic convergence, just like we saw in the optimal growth model. Okay, what I want to do today is at least get started. I'm not sure I'll be able to finish it because it's kind of a long-ish proof. I want to try to prove this proposition more formally than what we did on the diagram, okay? Now, here's the basic strategy that I want to employ to prove this, okay? Again, all of these different trajectories that we've described are consistent with optimality conditions 1 and 2, okay? There is only one trajectory, however, that is consistent with both 1 and 2, as well as the boundary conditions in this model, meaning that 1, the capital stock has to be non-negative, and 2, that the transversality condition is satisfied at infinity, okay? The way that I want to try to prove this is by basically showing that all of these trajectories in the picture will eventually violate one of those boundary conditions, except for one trajectory, and that is the saddle path. Okay, so this proof is kind of like a process of elimination type proof, that only one of them is actually going to satisfy all of the optimality conditions in our model. Okay, that means what we're going to have to do is actually prove that we can rule out. Now let's think about this for a second. What is true about any possible trajectory on the phase diagram, regardless of what the initial capital stock is? There's really only 3 places you can end up. You can either end up at the steady state on the saddle path. You can end up on a trajectory that eventually gets into region B. It either starts there and stays there, or it starts in regions A or C and eventually goes into B. Or it can be on a path that eventually enters region D, right? So either it starts in region D or it starts in region A and C and spills into region D. So there's only 3 destinations: region B, region D, and the equilibrium point E. What I want to do is show that we can rule out the possibility that any trajectory that enters region B or D is going to be optimal. All right, so that will be the first step of this proof, is to rule out paths that enter region B. Okay, let's suppose that our choice of K0 and C0, so we've kind of arbitrarily chosen the initial level of consumption, puts the economy on a path that eventually enters region B. Okay, it either starts there or gets there eventually. The subsequent path of capital and consumption is going to imply what? That consumption is increasing and that the capital stock is decreasing, right? But what this implies then is that the capital stock is actually going to hit 0 in finite time. That before time goes to infinity, the capital stock is going to hit what effectively is the 0 lower bound on capital, right? We know the capital stock can't be negative in this model, okay? And so once that occurs, then you're going to have some positive level of consumption and 0 capital. In fact, as consumption rises, the capital stock is actually going to accelerate towards 0. It's not going to approach 0 slowly. It's actually going to, so it's not going to asymptotically converge to 0. What it's going to do is it's going to slam headfirst into the 0 bound. All right. Now to think about why that occurs. So remember, remember what the second equation of our model looks like. Kt plus 1 is equal to 1 over 1 plus n times f of kt plus 1 minus delta kt minus ct. Imagine we subtract kt from both sides of this equation. Then the change in the capital stock between periods t and t plus 1 can be written as 1 over 1 plus n times, let me put this kt inside the brackets here. This is f of kt plus 1 minus delta kt minus 1 plus n kt. Well, that's just going to be minus delta plus n kt. So two of those capital terms are going to cancel, and then we have our minus ct. What do you see here? That the change in the capital stock is equal to some constant that's close to 1 times f of k minus delta plus nk minus c. What is this term? This term corresponds to the kt is equal to kt plus 1 locus, right? Where ct is equal to f of k minus delta plus n times k. So the difference between f of k minus delta plus nk minus c is the gap between consumption and how far away you are from the kt plus 1 locus, correct? So what that is saying then is that as consumption gets higher, it gets farther away from this locus of points, then the change in the capital stock is getting bigger and bigger and bigger, right? And it's declining, right? So the growth rate of capital is negative. So the higher consumption is relative to the kt equals kt plus 1 locus of points, the faster the capital stock is accelerating towards 0, right? So Ben, this may actually help answer one of the questions you had earlier. As we move in this direction, the capital stock is not kind of slowly converging to 0. It's quickly getting to 0 as consumption rises, okay? So eventually then, what that means is that the rule for determining the optimal capital stock is going to imply that the optimal value of kt plus 1 has to be negative. But we know that that's not feasible in the model because the capital stock can't be less than 0. At this particular point, once the capital stock hits 0, let's say that kt ends up being equal to 0 for all t bigger than or equal to tau. So tau is the time at which we kind of slam into the 0 bound here. Once that occurs, you're going to see immediately that the other equilibrium conditions of the model are going to be violated, okay? For example, what does the intertemporal Euler equation say? U prime of c tau, let's say, over u prime of c tau plus 1 is equal to 1 over 1 plus rho times f prime of k tau plus 1 minus delta. This is just the intertemporal Euler equation, right? Where I've brought the marginal utility of next period's consumption over here to the left-hand side. Now, the reason why I write this is that once k hits the 0 feasibility constraint, then what happens to the right-hand side of this Euler equation? You get a 1 over 1 plus rho times an f prime of 0 plus 1 minus delta. Well, what is f prime of 0 equal to? Infinity by the Infinity conditions. So this whole thing here is infinity. So the ratio then of the marginal utility of consumption today to what it looks like tomorrow is infinite. Well, that implies, obviously, that the marginal utility of consumption today is a lot bigger than the marginal utility of consumption tomorrow. And because the utility function is concave and continuous, that implies that C tau is a lot smaller than C tau plus 1. So what is happening here? As the capital stock is slamming into zero, it must be the case that consumption is rising dramatically, that the capital stock is accelerating towards zero and consumption is accelerating towards infinity, right? Consumption tomorrow is way bigger than what it was today. Right, so if I were to kind of draw the path of what consumption looks like here with respect to time, let's say, then it would look like this, right? Where this is period tau, the point at which the capital stock goes to zero. Okay, well, what do we know from the resource constraint? C tau is equal to F of K tau plus 1 minus delta K tau minus K tau plus 1. If we get to the point where the capital stock hits this feasibility constraint 0, then what is C tau equal to? F of 0 plus 1 minus delta times 0 minus 0 is equal to 0. Right? So we've got a violation then of the intertemporal Euler equation. It makes no sense. We're on a trajectory here where consumption is growing over time optimally as the capital stock is shrinking. But as soon as the capital stock hits zero, which we know it's going to do in finite time, what happens to consumption? It's going to go from here and immediately drop to zero and stay there forever. That is a huge violation of the intertemporal smoothing property of the Euler equation. You guys see what I'm saying here? I know this is more of a descriptive proof, but what I'm trying to get across to you here is that any trajectory that eventually enters region B is going to do first, it's going to imply that consumption is rapidly accelerating and the capital stock is rapidly approaching zero. But once the capital stock hits zero, which we know it will do relatively quickly, consumption is immediately going to drop down to zero. And that is going to violate the intertemporal Euler equation. So any path that leads ultimately into region B cannot be one that maximizes the representative agent's lifetime utility, because it will eventually violate one of the key equilibrium conditions. So any path that enters region B can be ruled out on that basis. It's not one that the family would choose. The family would never choose an initial value of consumption that puts them on a trajectory where they eventually enter region B, because in a short order of time, their consumption Euler equation is going to be violated. Consumption is growing smoothly, and then it accelerates, and then boom, you go all the way to zero. Part 2. Let's rule out paths that enter region B. Okay. First of all, I'm going to constantly be moving back and forth between this graph, so bear with me here. If we are in region D, then obviously consumption is falling and the capital stock is rising over time. We're moving in a southeast direction. So if we are on a path that is in region D, it is impossible for that trajectory ever to spill back into regions A or B, right? That's not going to happen. So let me first state that. Any path in D can't return to region A or B. Now, the reason why I'm saying this, let me be clear about this, is that in order to rule out paths that enter region D as being possibly optimal in this model, what I'm going to have to do is I'm going to have to show that every path that enters region D eventually goes to a single point in KT-CT space. Can you guys guess what that point is? On my picture here, any path that enters region D is ultimately in the long run going to converge to a single point. This point, I'm going to call that K bar. It is the level of capital that is consistent with the highest, it's the highest level of capital consistent with steady capital over time. Because it's what? It's the level of capital that is consistent with zero consumption in the long run. If you consume nothing forever, you can accumulate this much capital in the long run, but no more. The way I'm going to try to prove this is I'm going to show that every point, every trajectory that enters region D eventually has to converge to the same point. And that this point here necessarily will violate the transversality condition in the long run. Therefore, every one of these trajectories can be ruled out on that basis as being optimal. That's where I'm headed here. So the first thing is to state that any path entering region D can't possibly return to regions A or B. But the next thing I need to show here is that any path in D can't spill over into region C. That is not so clear, right? If we're moving in the southeast direction, it's not clear to me yet that we can't possibly spill over into region C, right? Couldn't we potentially do this? Let's say we're at this point. Couldn't we do this? Well, the answer is no. I want to prove that we're never going to actually enter region C as long as we're at any point in region D. That no matter how close you are to this locus, you're going to be moving towards this point. That will take a little bit of work. Okay, so how do we do that? Let me take some arbitrary point KT-CT that's in region D. Okay. Let me define K bar T in the following way. K bar T is the highest sustainable level of capital in the model. It's the one that's associated with zero consumption. So it's the point at which F of K bar is exactly equal to delta plus N times K bar. So if you take your KT locus of points and set CT equal to 0, you get F of K is equal to delta plus N times K. So K bar, the highest sustainable level of capital, satisfies this equation. And that should make sense, right? If capital gets so high to void, what ends up happening is because of diminishing returns, whatever you're producing this period is just barely enough to replenish depreciating capital and what depreciates due to increases in the population growth rate, right? So we've overaccumulated Ben so much that all of our output is simply replacing depreciating capital, and we're not consuming anything. That K bar is the highest sustainable level of capital in the model, and it's right here at this point where the KT locus hits the 0 axis. What I want to show here is if I start with some arbitrary point in region D, KT, CT in region D, that I want to show that KT plus 1, CT plus 1 also necessarily has to live in region D. In other words, it can never spill over into region C. Can I show that? All right, let's do that. Well, KT is less than K bar T by construction. If I've taken any arbitrary point in KT, CT space that's in region D, KT is going to be less than K bar by construction. Okay, that means that f of KT plus 1 minus delta KT is going to be less than f of K bar T plus 1 minus delta K bar T, because F is increasing in K, right? So K less than K bar implies that F of K plus 1 minus delta K is less than the same term evaluated at K bar. Let me multiply both sides of this equation by 1 over 1 plus n. So 1 over 1 plus n times f of k plus 1 minus delta k minus 1 over 1 plus n times f of k bar plus 1 minus delta k bar has to be less than 0. If I combine the terms here, I get 1 over 1 plus n times f of k plus 1 minus delta k minus f of k bar minus 1 minus delta k bar less than 0. Now let me add k bar to both sides of the inequality. That does not change anything. That doesn't change the sign of the inequality. But by doing that, it allows me to throw this k bar into the bracketed expression. And what do you get? 1 over 1 plus n times f of kt plus 1 minus delta kt minus f of k bar minus 1 minus delta k bar plus 1 plus n k bar t less than k bar. I'm doing this because some of it is going to cancel, right? Here's a minus k bar plus a k bar. So that one cancels with that one. And the whole thing can be written as 1 over 1 plus n f of k plus 1 minus delta k minus quantity f of k bar. And what are you left with? You're left with a delta k bar and an n k-bar. So if I take out a minus sign from the whole thing, it's a minus delta plus n k-bar t. You guys follow the arithmetic there? Yeah? No? Lost? What is this equal to?
KT plus 1.
F of k bar is equal to delta plus n k bar by construction. So this is equal to 0. So 1 over 1 plus n times f of kt plus 1 minus delta kt has to be less than k bar t. Well, if I were to subtract a CT on the left-hand side, the inequality is still going to hold, right? Because CT is strictly greater than or equal to 0, right? So I had this, right? But what I can do is subtract a CT over 1 plus n from the left-hand side, and the inequality is still going to hold because consumption is non-negative. Why does that help me? What is this equal to? What's 1 over 1 plus n times f plus 1 minus delta k minus c? That is kt plus 1. So we have that kt plus 1 has to be less than k bar t. So what have we established here? If we start with an arbitrary value of capital at date t that's inside region D, we've shown that kt has to be less than kt plus 1. And why do we know that? Because in region D, the capital stock is increasing. So if we're in region D, kt is going to be less than kt plus 1. But we just showed here that kt plus 1 is still less than k bar t. And because we're in region D, we know that ct plus 1 is less than ct, but still greater than or equal to 0. So we had the capital stock is growing, but bounded above by k bar. And we have that consumption is falling, but bounded below by 0. It follows then that kt plus 1, ct plus 1 must also be in region D. So it is not, it doesn't matter where you are in region D. If you take any arbitrary kt, ct point, we just proved that kt plus 1, ct plus 1 also has to be in region D. So it's never possible to be in region D and spill over into region C. Okay, so we have established that any path in D can't return to regions A or B, and we've established that any path in D can't spill over into C. The last thing we need to establish, and I won't.
Wait, so that shows both of them, that shows the 1 and the 2?
Yes.
Okay.
Well, we know we can't go into A or B because we're moving southeast. So going into A or B is not possible by moving southeast. But moving southeast, it's still possible to go into region C. But what we did for number 2 here is we just proved that if you're in region D, you can't spill over into region C. We proved that more mathematically. The last thing we need to do is we need to say that all paths entering D must eventually converge to K bar and 0. Okay. If you were to take an arbitrary point in region D, some KT and CT, then what have we already shown? That KT plus 1 and CT plus 1 also have to be in region D, where the capital stock is bigger, but consumption is smaller. So once we're inside of region D, it's not going to be possible, if we're moving in this direction, it's never going to be the case that suddenly the path of consumption and capital is going to stall out before we get to this point, right? If we're anywhere over here, we're going to continue to move in a southeasterly direction. We're not going to get to a point where the trajectory just runs out of steam altogether and stops before we get to this point K bar, right? Because if we're at that point, capital and consumption are going to continue to move in this direction. But what could possibly happen here? We could be on a path where before we actually get to point K bar, we run into the 0 axis. Like this. Now, what do you think happens once we get to that point? Let's say we started here at point 4, we crossed the C locus horizontally, and then we quickly got to the 0 axis. What do you think is going to happen at that point to the trajectory of capital and consumption? Consumption is going to stay at 0, but the capital stock is going to climb every period until it gets to that point. So you have some of these paths that go like this, but you're also going to have paths that go like this. Right? How can we demonstrate that? Well, let's assume that the 0 axis is hit, okay, at some point. So let's say CT is equal to 0 for all t greater than or equal to cap t less than infinity. So we're on a trajectory that enters region D, but unfortunately we hit the 0 axis before we get to K bar, okay? Well, what's going to happen subsequently? Well, 1 plus n times kt plus 1 will be equal to f of kt plus 1 minus delta kt. That is simply the intertemporal solvency condition or resource constraint where we had set consumption equal to 0 forever. Well, that just means that 1 plus n times the change in the capital stock between t and t plus 1 is just equal to f of kt plus 1 minus delta kt minus 1 plus n kt, which is just f of kt minus delta plus n kt. In other words, the growth rate of capital, basically, is equal to 1 over 1 plus n times f minus delta plus n times k. We know that this is going to be positive for any k less than k bar, because once k gets to k bar, f of k bar is equal to delta plus n times k bar. So the capital stock is going to grow, And we can look to see what the dynamics of the capital stock are going to be by graphing these two components of the growth rate of capital, right? If I were to sketch this graph real quick, where I've got, let's say, this here is, this is f of k divided by 1 plus n. This here is delta plus n over 1 plus n times k. Then the intersection of those two functions is going to correspond to k bar, right? Where f of k bar is equal to delta plus n times k bar. Well, if we take any k, let's say evaluated at date cap t, that's the point at which consumption is equal to 0 forever, then what do we see? We see that f of k is bigger than delta plus n times k, which means that the growth rate of the capital stock is going to be positive. As long as f of k is bigger than delta plus n, the capital stock is going to be rising. If it turns out that f is less than delta plus n, then the capital stock is going to be falling. So what this means is that in the long run, the economy is going to converge to k bar if consumption stays equal to 0. So any trajectory that enters region D that slams into the 0 axis is just going to see the capital stock rise over time until what happens? Until the amount of output that we're producing every period is just enough to replenish the depreciating capital and the capital that gets spread more thinly across the population due to population growth. Therefore, any trajectory that eventually enters region D has to go to 1 point and 1 point only. K is equal to k bar and consumption is equal to 0. Now, I don't have enough time to prove this today, but what I will do for the first, let's say 30 minutes of class next Monday is I want to show that this particular allocation, okay, in region D violates the transversality condition. So any trajectory that enters region D and therefore has to go to this unique point is eventually going to violate the family's transversality condition. So it cannot be the optimal, it cannot be an optimal trajectory over time. So we can rule out then any path that eventually enters region D. That leaves only one possible trajectory for consumption and capital over time, and that is the saddle path solution. So we'll have proved its existence and uniqueness essentially by process of elimination. That'll take about a half hour, I think, and then we will be done with that, at which point we can switch gears and start talking about stochastic dynamic programming. All right, and that's probably going to take about 2 class periods to go through all of that, and then we'll move on to the Brock-Merman model. Okay, test next Friday. Yeah.
Do we have a time set for that?